So hello, my name is Oliver Cartus from Gamma Remote Sensing in Switzerland. I'm part of the CCI Biomass team, and together with my colleague Maurizio Santoro, I am responsible for producing these global above-ground biomass maps that have been released in the first 3 years of the project. And in the next few minutes, I'm going to talk about how these maps are produced, which data sets we use, what the methods are, how the maps are validated, and also we'll talk about the possibility or the limitations of quantifying change at annual and decadal intervals. So Richard already discussed a bit what kind of sensors there are available from space that provide information that's relevant for mapping biomass of forests globally. So in this project, we primarily rely on C and L-band radar data that has been collected by a series of ESA and JAXA, so Japanese satellites, in the last 3 decades, actually, so more or less continuously. And they provide very valuable time series of observations. They don't measure biomass, they see different aspects of forest structure. So C-band is a shorter wavelength radar that sees more foliage and small branches. L-band is a longer radar, the longer wavelength radar that sees more the larger branches to a limited degree. The stems, so that can be related to biomass then. We do consider optical data like Landsat, MODIS, but mostly to support the radar modeling. It's not directly used to map biomass. It's there to support the mapping with radar. And we also consider LiDAR data, spaceborne LiDAR data. So in the first phase, we've mostly looked at ISAT glass data that gives us very detailed information about the vertical structure of forests. And that's also used to inform the modeling of the radar as functional biomass. So one of the 2 main data sets we use for mapping is C-band backscatter data that has been acquired in the past by the ESA Envisat ESA mission. In particular, in a mode that was called ScanSAR, there was a lot of multi-temporal data acquired, not entirely globally. There are some gaps, but for the epoch 2010, that's an important data set to work with. Since 2014, when Sentinel-1 was launched, we have a much denser multi-temporal time series of C-band backscatter observations from the so far two Sentinel-1 satellites. So for each year, at least since 2017, we have more than 250,000 observations per year. And at each location, at least 30 observations per year, which is very important to make use of C-band backscatter data. All of this is being processed on AWS. It's a lot of data, but also worth it. With respect to L-band, so the longer wavelength radar, we've been working so far with the mosaics that JAXA has released based on a high resolution called fine beam mode. Working with mosaics is not our preferred mode of operation, but so far the data has been available in this format. Some years ago, JAXA also provided images that have been acquired in another imaging mode called ScanSAR. There we have multi-temporal observations, at least over the tropics. So we have, in each season, we have observations, which is also very important to make good use of the data for biomass mapping. In future, JAXA will also provide us access to the individual images so we can process them ourselves. So that should help to get rid of some of the calibration issues and geolocational issues that have been a problem in the mosaics that have been released. So we hope we can improve this further and make better use of L-band in the future. So with respect to the algorithm, the core algorithm has been referred to as Biomass, which has been adapted for C and L-band. A main feature of this algorithm is that it doesn't rely a lot on in situ data for calibrating models. So in this algorithm, we calibrate semi-empirical models that relate backscatter to C and L-band backscatter to biomass. But that's done mostly without using in situ data, which is an important feature for global mapping algorithms, because in large areas of the world, we simply don't have in situ data. And these backscatter to biomass relationships, they vary a lot, spatially, but also temporally with different imaging conditions. It makes a difference if if the images have been acquired under wet or dry conditions, frozen, unfrozen, so that needs to be considered. So in this algorithm, for each individual image we have, so several 100,000, we do estimate biomass individually. And in the end, we calculate, or we combine them multitemporally and across the two different frequencies, considering the strength of the biomass signal we have in each individual measurement. So to get an improved best possible estimate in the end. And all this is done at 100-meter resolution. So the model that we use here to relate backscatter to biomass is a simple water cloud type of model that has been reformulated in two different ways. It can be used to relate to forest structural information like canopy density and height, but there's also a version of the model that relates then backscatter to biomass. And the way this works here is that we calibrate the model with the aid of optical canopy density maps. Canopy density could also come from LiDAR or like JEDAs. So far it's been optical products. And then the model that relates backscatter to biomass is inverted using the parameters that have been determined before for each individual image in a multi-temporal stack. So it's a very flexible framework for adjusting the retrieval locally. So we can adjust everything at very local level here. Okay. The LiDAR data gives us a lot of information about forest structural differences around the globe. Specifically, we looked at relationships between canopy density and height, and between height and biomass. And so there's a database of different elementary relationships around the Earth, and that informs the radar model. So that allows us to adjust the models to different forest structural characteristics. So far we have produced maps for 3 different years, 2010, 17, and 18. And each of the maps is accompanied by a standard deviation map. So that gives the user information about the precision of these estimates. Currently, we have version 3 of the maps. So the workflow in CCI Biomass is that every year we reproduce maps, hopefully improved maps, and also add maps for additional years. And that will continue also in the second phase, which started a few months ago. So currently we have version 3 and these 3 different years. There has been an independent validation has been performed with about, I think, 120,000 in situ inventory plots from different networks, national forest inventories, and so on. That's not a systematic sample around the Earth. It's rather opportunistic, so it doesn't follow any systematic sample design, at least globally. But that's what we could get hold of in the end, what reaches certain accuracy standards. In addition, we also considered statistics that are reported at national or subnational levels. And what we see that at global scales, the estimates tend to follow well the one-to-one line, at least on average. The global distribution is well represented. But of course, when we look more closely in different regions, we do see biases, so systematic over or underestimation. And it's a continuous process to understand these biases and improve the maps with each release, so every year. So that's going to continue. And the biases also differ between the different maps, in particular between 2010 and 17, which currently affects how well we can detect changes when we take the simple difference between these maps at annual or decadal intervals. So changes associated with clear cutting are usually well captured. You see that here in the example in the Chaco in Paraguay. But beyond clear cutting, the changes we see, we cannot really verify. There's very limited information so far to validate the differences. And we are also aware that in many areas, we do see differences between 2010 and 17, 18 that seem rather unrealistic. We do provide additional maps that serve as sort of a quality flag. So they indicate the reliability of these changes. And to be honest, at global scale, most of the changes we see beyond clear-cut events have to be considered rather unreliable. The reasons are manifold. One major reason is that we don't have the same amount of data in 2010 and 17, 18. So there was much less data to work with and to reduce biases in the 2010 map. But of course, so some of you may be aware that backscatter does have limits in the sensitivity in high biomass ranges. So the signal is rather weak, and even small errors we make in the modeling can translate into rather big biases between the maps. So in the next phase, we will continue. So in the next 3 years, we will continue to improve the interannual consistency of the maps and also adjust them locally to improve them locally, the statistics. And each year we will also add additional years. So far we have 2010, 17, and 18 actually. And the next years we will produce a complete series of maps for the timeframe 2015 to 22, and also for 2007, and maybe also going back to the 1990s. In this context, also user feedback is very important and is strongly encouraged. As I said, the modeling framework is very flexible, so we can quite easily adjust the modeling very locally if users report errors, artifacts, whatever problems in the maps. Okay, so that would be it from me.